All right, this video is going to go through pages 9 through 11 in your circular motion packet. We're going to go over centripetal force. So according to Newton's second law, the acceleration of an object is caused by an unbalanced, let me turn my pen on first, an unbalanced force acting in the direction of the acceleration. So if an object is moving in circular motion, it is accelerating and thus must have an unbalanced force causing this acceleration. So remember, it can be accelerating two ways. Is one, you can actually increase or decrease the speed, or you can change direction. And since if you're going in a circle, you're always changing direction, that's what makes you accelerating. Now, centripetal force, Fc, is any force that is causing centripetal acceleration. Fc is always directed towards the center of the circle. Okay, and that's going to bring us to our equation F equals ma. Okay, so all we're doing now is we're still using Newton's second law, but now we're just adding these little c's for circular motion. So that's centripetal force equals mass times centripetal acceleration. So if acceleration is pointing one way, so let's just say this is our circular motion, okay, and then our acceleration is pointing towards the center. If AC and FC are in the same equation, that means force also has to be pointed towards the center. That's one way to remember it, is if they're in the same equation, they're going the same way. Now, examples of different forces being centripetal force is one, a ball on a string is rolled around in a circle. Okay, so I have a ball being whirled around in a circle. Okay, that would be example, that would be tension force. Okay, so that tension is what's keeping it going in that circular motion. Number two, a person runs on a curved section of a sidewalk or track. So I have a curved section of some type of path. And what's keeping that person going in that curve is friction. Okay, so friction is what's keeping you on that curve. So you think of like driving and stuff, is when you start taking away friction, it's going to be harder to stay on that curved path and you may go off that path. Three, a planet orbits the sun. That is going to be your gravitational force. Okay, so the sun is using that gravitational force to actually keep you in orbit. And then number four, a car turns through a curved section of the road. So again, the same concept. Okay, is you have friction that's trying to keep you in the center. Okay, or keep you along that path. And if you don't have that, then you're not going to stay on that path. Example, I have a 1,000 kilogram car. So there's your mass. Enters a level roads curve at 20 meters per second. There's your velocity. If the curve has a radius of 80 meters, so there's your radius, and meters is what you want, so we don't need to fix anything. How much centripetal force is needed? So you're looking for Fc. Okay, so Fc equals mass times AC. Now, we have mass, we do not have AC, so that means we're going to have to go and find AC. And we do know that AC equals V squared over R. So velocity in this case is 20, so 20 squared over your radius, which is 80. And that comes out to an acceleration of 5 meters per second squared. Now you know your acceleration, so we can come back over here. So we're going to take our mass, 1,000, multiply it by your acceleration, which is 5, and you're going to get a centripetal force of 5,000 newtons. So remember, your units for force is newtons. Now in this example, tire traction or friction with the road is the centripetal force in this example. Without it, what would happen to the driver when the driver tried to turn the car? So think of your road like this, and now all of a sudden, so here's it is on a dry day. Okay, friction is keeping you in that path. Now you add rain or anything like that, and all of a sudden now your friction starts kind of going away. So that means you're not longer going to go on that path. You're going to start following whichever direction you were pointing. Okay, so without that friction, you're not going to be able to stay on that path. Now, centrifugal effect, objects want to stay in constant motion in a straight line because of inertia. So remember, inertia is mass. The more mass you have, the more you want to keep going in that direction. When moving in a circular motion, the feeling of being thrown or pushed to the outside of the circle is called centrifugal effect. Okay, so this feeling originates from Newton's first law. Objects want to keep moving at a constant velocity in a straight line. So think of like an example is like this would be like your carnival rides where a person stands here on the wall and you start spinning around and around, okay, and then they actually drop that floor out from beneath you. Instead of falling, what happens is that centrifugal effect is pushing your body against the wall, okay, and it keeps it against that wall. Therefore, following this first law with inertia, your body wants to keep going in that direction, so that's why you're pinned up against that wall. So moving on to the next part. So the speed of an object in uniform circular motion remains the same. So that means we're spinning something around. Uniform means constant or not changing, so our speed is going to stay the same. Now number 2, it says linear speed. So linear speed is the speed in a straight line. Okay, we're looking at point A and point B right here. So we're going to say point A and point B are attached to a string that's being spun around. If I were to take A's path and put it into a straight line, so A's path kind of looks like this. You're going around and around. So A's path would probably be something like that. Now, if you were to take B's path has a longer way to go. Okay, so if you were to look at both of their lines and both of them get through that line in the exact same amount of time, you'd want to know, well, are they going the same speed? Is one going quicker or one going slower? Well, if both of these are covering that in the same time, that means B's got to be going faster, because if you notice, B's got more ground to cover in the exact same amount of time as A. So linear speed is not the same. Okay, so just think about linear would be a line. If you took their path, made it into a line, okay, would their lines be the same? No. Now, angular speed is different. Angular speeds means that every angle, would it be the same? So if I did 45 degrees, 90 degrees, whatever these degrees are, A and B would still always be right in line with each other. Okay, so that would never change. So angular speed would stay the same no matter what. Okay, 4, the linear speed on a rotating surface is the same at every point on the surface. So we just talked about that in number 2. That means if I start picking different points on this circular motion, they're all going to have different linear speeds because they have different amounts of ground to cover. So this is going to be false. Number 5, an object moving in uniform circular motion is accelerating. So remember, there's 2 ways to accelerate. One is you're either speeding up or slowing down, or 2 is you're changing direction. Okay, and since you're always changing direction in a circle, this would be true. An object moves in a horizontal circular path, okay, with a uniform circular motion. Draw and label the vector to show direction of object would move if it were to stop moving in a circular path. Basically what that means is I'm spinning an object around, so we'll say this is my object, and we'll say I'm spinning it around clockwise. And let's just say that object were to stop moving in a circle at that point and just keep going whichever way it's going. That means velocity would just keep going tangent, okay, to that circle. Okay, so think about this like a slingshot, or we talked about tubing in class. If you were to fall off a tube behind a boat in a circular path, which way would you go? You're not going to keep going in a circle. You're going to just go straight in the direction you came off the tube at. So that'd be your answer for number 6. And then number 7, we're just going to basically do a recap. So we're spinning something around. So we'll say this is our object, and we're going counterclockwise. Okay, velocity is going to be tangent to the circle, so velocity would be going this way. And then your centripetal acceleration and your centripetal force is always pointing towards the center. So no matter where that object is, okay, your object could be here. A, C, and F, C are going to be pointing towards the center, and then your velocity is going to be tangent. Okay, so that's going to end that one, and we'll do more practice on the next one.